Hi, everyone, and welcome to the Machine Learning Summer School. And I hope your previous sessions went well. And today, now I'm going to talk about the modules 2 and 3 for the topic of unsupervised learning. So let us begin. So this is what all that we are going to talk about. You've already heard from my colleague Ayush Raj, where he talked about various clustering methods. And the essential idea is that the data that we see in the real world, it has a certain structure. Okay, and therefore the idea that the data would cluster in certain ways, and finding out which data clusters together versus which samples cluster far away from each other might be useful for us in applications. So anyhow, I'm going to continue from where we left off from Ayush. And just a brief introduction about myself. My name is Dhruv Bharadwaj. I'm an applied scientist too at Amazon, India. And most of my work is related to automatic speech recognition for Alexa line of devices. And so let's begin. And so these are the topics that we are going to cover. We are briefly going to talk about the notation that I'm going to use. So this section is going to be slightly mathematically involved, while I'll try to walk you through almost everything that I've written in the slides. And the intent to keeping it a bit mathematical is to ensure that you, if not now, maybe later when you revisit these videos or when you study on your own, you tend to get comfortable with the mathematics of these models to a certain extent, or maybe you can revisit these slides later on and appreciate the mathematics once you are more comfortable. So, yeah, let us begin. So, these are the notations that I'm going to use for most of my slides. You have capital X, which is your set of training data. So what I'm saying is that capital X is basically a set of all these samples X of I, where I is 1 to n. So n is the number of training samples. And each x of I, right, is probably a d-dimensional vector. So it is a vector of real values. So this is a very common example that is given for real valued vectors. Is if suppose you have a grayscale image and each pixel has an intensity, then you stack the columns of that image to form a very very long vector. So and that could be so the set of images is your training set, and each image is a very very long vector. And similarly, although we are in unsupervised learning, this Y may probably not occur, but just for completeness, this may be a label or target set. So corresponding to each xi, you have a yi, which is just a real scalar, or which is a label corresponding to the ith training example. Then we will talk about latent variables. I'll explain what latent variables are. And there, corresponding to each xi, I may talk about a zi. Again, it's probably going to be a scalar, at least for the initial part of this module. Then we use the notation p of x or p of y to denote the probability density functions or distributions. And compared to your undergrad or the notation which is used in standard books at undergrad level, we are not going to distinguish, write different px of x or py of y to denote these densities or distributions to distinguish between them. The way they get distinguished is by the argument. So p of x is a distribution over x, p of y is a distribution over y. Although I use the words density and distributions interchangeably, they will always mean probability density functions. Okay, so we will make this assumption that for our data, the probability density functions exist, and we will proceed accordingly. So I will also have a distribution which has a certain parameters. So for example, mean and variance of a Gaussian normal distribution are its parameters, and I will denote such a distribution like this. So you have a distribution over x, which is given by p of x, and its parameters are theta. So you have a semicolon and theta are all the set of parameters. So for example, all the values of the mean or the covariance of a Gaussian are put in a vector, and I denote that vector as a theta. Now, this is also an important notation, very common in this community, which is it comes from conventional statistics. Is We denote x tilde p of x to mean that we are sampling a value from a given distribution p of x. Okay, so this basically means that, for example, if suppose your p of x is a Gaussian normal, right? You have something like this. You have a normal distribution, not a standard normal, but a Gaussian, and you have x. So, so these are the values where p of x is high, right? So that means that these x's are more likely to occur. So there are standard numerical techniques to sample from these from the standard Gaussian distribution with a given mean and variance. And what you do is, if you are sampling x from p of x, it means that you are picking this value x of 1 or x of 2 and returning it. Okay, so this is the essential idea. And finally, an expectation is defined as expectation, this E of P of X of F of X. So here, essentially, I am taking the expectation of this function of X with respect to the distribution P of X. Okay, so this is your standard undergrad level definition of an expectation of a function of random variable, right? And finally, uh, uh, compared to undergrad, the only thing that is extra is this particular subscript that I'm using, which basically says that the x follows a distribution p of x, and we are taking expectation of a function of x. Okay, so this is a standard definition of expectation. Now, expectation, although written like this, it will almost always be computed empirically. Okay, so you can think of it as being written like this, but actually being computed like this. So what you would do is, if you know p of x and you know how to sample from it, you take out many xi's from here. You evaluate f of xi for each xi, and then you take a empirical mean. So this is how you would usually compute it. So a side point on why we are talking so much about p of x's and so on is the idea that uh, uh, your data, right, it basically follows a certain distribution. Okay, and when I say that it follows a certain distribution, if you what I mean is, if you think of all the images in your training set, now those images will have certain characteristics. If they are images of faces, right? The the images in which the mouth appears below the nose, okay, are going to be very likely. Whereas the images where the mouth appears above the eyes, even in a straight orientation, is highly unlikely. It's almost impossible in natural face images, right? Unless you have some fantastical fantasy images being generated from somewhere. So essentially, your data follows a certain distribution, right? We can put a distribution on this data, and this gives us a very powerful way, a framework of probability and statistics to manipulate this data, to understand this data. And the mechanism that we will use to understand this data is through neural networks, okay, which can basically learn more about this data and incorporate information about this data through our techniques and backpropagation. So with this, let us begin. Okay, so let us first talk about Gaussian mixture models and expectation maximization. So Gaussian mixture models, you might have seen them before. They are almost always introduced as models which can estimate any arbitrary density. So you have some data distribution P of X which is given, what you want to do is you want to take many Gaussians and you want to mix them together so that they are very close to this distribution. Now, why do we want to do that? We are interested in P of X of real life data, but they have arbitrary distributions. I mean, they must be having very complex distributions. It's natural to assume that. And it is also unlikely that simplistic distributions like Gaussian in continuous or other Laplacians and so on, they will model this data very well. Okay, and therefore what we can do is we can produce complex distributions by combining arbitrary number of Gaussians and adjusting their means and covariances. So one example of arbitrary uh, distribution is this uh, figure that I've shown here. So you can see that here there is a peak. It's not naturally a Gaussian. In fact, I've created it from a mixture of Gaussians, but I think you see the point, right? So there is no natural distribution which can actually uh, model this arbitrary P of X, and therefore we would like to have something else, right? So even in case of so for example, you have learned about clustering, and if suppose in a two-dimensional landscape, right, you have a two-dimensional map and you have some data which is clustered over here and you have some data which is clustered over here. So when you, for example, do k-means clustering, right, it will give a cluster k1 here and it will give a cluster k2 here, but there may be samples here, right? What do you do about that? Okay, if you do k-means clustering, then based on some heuristic, essentially a distance function, it will do what is known as a hard clustering. So it will basically decide that, okay, based on my understanding of this data, this sample must go into k2 and this sample must go into k1. Okay, whereas in Gaussian mixture models, what you would do is what is known as soft clustering, right? So here you would have a Gaussian here, and here you will have a Gaussian here. So what it's saying is that roughly this sample, right, 20% of this has a contribution from this, and maybe some other percentage from here, right? So that is the idea. So it tends to do some sort of soft clustering, and therefore it is able to model the regions of low data probability much more better than doing this kind of hard clustering. Okay, so this essentially defines our Gaussian mixture model. Okay, you have p tilde of x, okay, which is essentially a weighted sum. So these are your Gaussian normal distributions with means mu k and covariances sigma k, and they are weighted with a weight wk, and k or capital K of them are summed together. Okay, so that's all. It's as simple as that. And now the parameters of our model are now the means and covariances of each of the Gaussians in the mixture, the weights of the Gaussians, and the number of Gaussians that you're using. And essentially, if I'm defining a mixture model over my data as this, then it is these parameters theta which need to be estimated. So now our problem becomes this. The problem of estimating the P of X of data becomes the problem of estimating, given a few samples from the data set D, that is X of I, I equal to 1 to N, we want to estimate parameter theta, and we want to do it using maximum likelihood estimation. And what we will see is that it is the expectation maximization algorithm which enables us to do exactly that. So, but before coming to EM, I want you to I want you to look at another view of Gaussian mixture models, and we'll go to that next. So Gaussian mixture models can also be seen as latent variable models, and this is a family of models. And the idea of latent variable is also not new, but at least I think that it's a pretty powerful idea. So what we assume is that the data that we have observed, our training set, right, it's only part of the data. The underlying physical mechanism which generated that data is anyway may not be known to us, right? It may be too complicated for us to, define it exactly. So we say that there is an underlying true state of nature which is hidden and which we model as latent variable z with a distribution p of z. So all I'm saying is that there is some underlying true state of nature, okay, and I am modeling it like this. Okay, somebody else may have probably model it in some other way. Okay, what I am saying is that the underlying state of nature is a discrete variable. It's this discrete variable z, and it has a distribution p of z. So for example, z may, for example, just take two values. So z is there, it may just take two values, maybe z equal to 0, z equal to 1. It may take the value 0 with 0.2. It may take the value 1 with 0.8, right? So this becomes your p of z. So it's a simple discrete variable which has some p of z defined like this. Okay. Now, so what we say is that if it is this latent which generates the observable data, so this idea of generation from latent is very powerful, and together they form the complete data. So for now, understand that I am saying that there is a latent, okay, and I am saying that this latent generates this data. Uh, uh, so it's basically a mathematical assumptions that it's a mathematical model that I'm building, okay, to explain my data. Okay, so now if I say that it is this z, right, which is the latent variable which is generating the data, then I can definitely write this, right? I can definitely should be able to write this. All I am saying is this, that if I have a complete data which is given by x comma z, right? X is what you have observed, Z is what you have not observed, but complete data is x comma Z. Then P of x comma Z is the joint distribution, right? Now this P of x comma Z, when you marginalize over it, you get P of x. Okay, so all I'm doing is I'm averaging out the Z from it. Okay, and this is all I've written in here, right? This P of x comma Z is further broken down into P of Z, which we have already, although we don't know about it, but let's see. So now you see that this makes our modeling explicit. We say there is a Z, okay, and once a Z has been chosen, a X is generated, okay. So now I give some specific form to all that I have written here, right? If suppose my P of Z is these pi k's, so this is similar to the 0.2 and the 0.8 that I had created right now, I had plotted right now, and the P of x comma z, x given z, are the normal distributions. Okay, in that case, this equation can simply be written like this. Okay, and again, what we have is a Gaussian mixture model, and the only difference is that the weights are these probabilities. Okay, and the that's all actually, right? So what you see here is that you have some different meaning given to these weights, okay, which is the probability that your latent variable z takes the value k, right? And this is very common to many. This formulation is common to many latent variable models in that family, and Gaussian mixture models are all can also be looked at from that point of view. So now this abstraction is very important. This idea of a latent variable z, right? It is very important. It helps us do two things. One is generation and the other is discovery. Okay. So what do I mean by generation? I've already explained it. Okay. If suppose I want to generate a sample from a latent variable model, what would I do? Okay. I have some z and I have some distribution p of z. Okay. Again, what I will do is I will do I will first sample z from p of z. Okay, and for suppose that value is given by z naught. Okay, now corresponding, so whatever, if z naught is equal to k, right, I will take the kth quotient. Okay, and I will sample from it. So basically x will be sampled from your normal x mu k and sigma k, right? So this will happen. So basically I have a systematic mechanism of generation. Okay, and that becomes very important in certain conditions. And similarly, you have the idea of discovery. Okay, if suppose you have a data set d, which is of x size, right? you may want to learn a latent variable corresponding to those. So this latent variable, right, it may give a structured or a compressed form of X. So for example, we'll talk about VAs later, but VAs, for example, give you a latent vector, okay, a latent Z, which is smaller in dimension as compared to their input X, okay, and we force the VA, we train the VA in such a way that so that the Z only contains the useful information for our task or for preserving the input. Okay, so that way Z can represent a compressed form of X itself. So this is very important. So what we'll see is that this idea of latent variable, right? This also simplifies the mathematics behind the EM algorithm because we'll be able to, define everything in such a way. So let's get to that now. Okay, so let's first, take a recap of what we have done in the past and what we are going to do. So in supervised learning, what we do essentially, okay, I'm just summarizing it in one sentence. What we do is we maximize the likelihood of observed data. Observed data is the training set in our case, okay, and the parameters of the output distribution are encoded in the neural network. Okay, so essentially what it does is the neural network itself is essentially learning this, uh, this P of y given x using maximum likelihood. So you have P of y given x, okay, which is going to be learned, okay, in a certain way. Uh, Now, in case of unsupervised learning, right, our observed data is modeled as this P of x given theta. Okay, and what may happen is this P of x. So, for example, it may be a complicated distribution, right? Even when we model it using GMM, right, it's a mixture of many Gaussians, right? So, it's not always possible to compute exact likelihood. Okay, let me just write what likelihood is. Okay, so your likelihood of theta is a function of theta. Okay, it is going to be the product of I equal to 1 to n P of x of I given theta. So what I've done here is that I assume that there is some p, okay, which is parameterized by these parameters theta. So for example, a Gaussian mixture model with some means, variance, and weights. Okay, and I take each of my training sample and I evaluate this quantity. Right, I'll plug it in. I'll evaluate it. Okay, now for some values of theta, right, and I'll take the product. Okay, so for that values of theta, that this will be my likelihood, and we usually work with log likelihood. So you'll have log of L of theta, and this whole thing becomes a summation because of a log, and you have this, right, so you have this. So now you can see, right, you have this entire quantity, and if P of xi given theta is complicated, right, it may not be possible to compute this. Okay, it may also not be possible to maximize it. Okay, so in case of Gaussian mixture models, for example, we may be able to compute it, but maximization is a different deal, right? So now what we do is, instead of trying to compute this quantity and maximize it, all we do is we approximate. Okay, we do this latent variable modeling and we use expectation maximization to approximate this likelihood. So we just want to approximate this quantity. Okay, and then we want to make sure that if we are approximating, once we have approximated it, we try to increase it. Okay, because that's the idea, right? Learn theta by maximum likely by increasing the likelihood of the observed data. Okay, so that's the idea. So we look at expectation maximization for as a general technique for ML estimation of parameters of latent variable models. Okay, so in our case, theta, when we have these GMMs. So this theta, if you remember, consists of your WK, mu k, covariance k, and capital K. Right. So this whole thing is theta. We want to estimate all of this. So, although I could have chosen to actually just, you know, taken Gaussian mixture models, introduced a Z, and then done some mathematics to derive the equations for the E and M step of expectation maximization in case of GMMs, it doesn't give you this intuition that EM actually applies to other latent variable models as well. Okay, and whatever is being done in EM is not just some mathematical trickery where, for example, you may have been told that we want to convert log of sums to sum of logs, right? And that naturally happens. Okay, but there is also something more that gives a better intuition. So that's what. So while closed form iterates of EM on GMMs can be derived, this view will probably give you better intuition of what is happening. Okay, it may be a little complicated to follow, but I hope that if you go through the equations carefully and possibly also look at other resources online, it will give you a better idea of what is happening. So let us continue. Right. So let us now begin with expectation maximization, and I will reiterate what we are trying to do. Okay, we have the observed data X. We have the observed data X, and it is generated by a latent variable Z. This is what we said all along. And therefore, if you have the joint distribution P of Px comma Z, then you can sample X comma Z from here. Okay, so this is the complete distribution, right? But what we are interested obviously in this one, right? And we want to find the correct theta. Okay, so once correct theta has been found, P of X given theta basically mirrors the actual P of X, right? So we have two requirements, right? We want P of X given theta star, which is the correct theta, right? The ideal theta that we have found to be almost same as P of X, okay? True distribution. And we want to be able to do this, right? Right. So we want to be able to we want to be able to generate new samples from this, right? So this is the overall aim. In fact, you'll see me repeat this multiple times. This is going to be the overall aim of all of generative modeling. So now I do something very simple, right? We already had P of X comma Z, and I'm only marginalizing out Z out of it, and you get this P of X, right? So this is all that is done. Only theta is there because we are working with an assumed model, right? We are working with maybe something like a GMM, which has certain parameters. So just the parameters are explicitly shown here as theta, right? So now with this, let us see what happens. So now let us suppose we are given this data, okay, and I use the previous marginalization as well, right? So uh, you write your log likelihood, right? We had written our log likelihood like this. Uh, Give me a moment. Yeah. So now in this particular slide, I'm denoting log likelihood like this with a capital X, where X is your data set, right? So I can write like this is summation over all xi um, log of p of xi given theta, right? And now in the previous slide, we already saw that p of xi given theta can be written by marginalizations, right? So we take that and plug it in, log of, again, a summation of uh, p of, so this is a summation over z, maybe zi, because every xi has a zi, right? So now you see that the only thing that I've done in the So this is what I was writing as ln of L of theta. Okay. So the only thing I have done here is just assumed a Z and redone the marginalization. And already you can see the problem. If I want to maximize this, okay, if I want to estimate this, there is a log and a sum which is present here, right? And with Z, this will get simplified, and this is how the whole thing is motivated in general. Okay, but we want to do more. Okay, so uh, you know that for this latent variable Z, right? Although we said that Z comes from a P of Z, if I just have assumed a Z, okay, I actually have no knowledge of this P of Z, right? But what I can do is, again, one more extension. Okay, I assume that it is Q of Z. Let us suppose that there is a Q of Z which is very simple and which I can sample from. So I can have Zi coming from Q of Z. Okay. So what I will do is I will introduce this Q of Z in this equation. Okay. And I will write this. So we have summation with respect to Zi, Q of Zi and P of xi Zi theta by Q of Zi, right? So I'm just introducing it and then I am doing some mathematical conversions. Okay, so all I do is I do some mathematical conversions. Okay, and with that you will reach at this equation here. Okay, where you have two things. Your log likelihood is here. Okay, log of L of theta. Okay, and this is another quantity that I'm going to talk about soon, and this is a KL divergence between Q of Z and P of Z given X. So this makes sense, right? I don't know anything about P of Z. Okay, so I assumed a Q of Z, but I would like Q of Z to be as close as possible to P of Z given X. Okay, so whatever the P of Z may be, given X, Q of Z should be as close as possible to this. So, so essentially, I have reformulated the equation for my log likelihood having a certain this quantity and a KL divergence between a term that I don't know much about and a term that I have assumed. Okay. Now, with this, you know that this quantity is always going to be greater than equal to 0, right? So what that means is that you always have this. Your log likelihood is always greater than equal to this. Sorry for the unfortunate choice of symbol. This is not log likelihood. Okay. When I write q comma theta along with it, this is what is known as elbow. And the reason is clear. It is only because of this equation that this is called elbow. This is the evidence, and this quantity is the lower bound on evidence. Okay. So, so if you actually do the mathematical derivation of introducing Q and then simplifying this equation, right, you will see that your evidence lower bound is just written like this. Okay. So, so essentially what you are doing in evidence lower bound, right? You have some distribution of Z from which you can sample nicely. Okay. So you sample some Zs from here, then you can compute this, you can compute this, okay, and you can compute this. Okay, makes sense, right? So this L of Q of theta is computable. Okay. The only thing is we need to find the right Q and we need to find the right theta. Okay. So uh, given this equation, I should be able to draw this diagram. Okay. This is my actual log likelihood. Okay. This is my elbow and this is my KL divergence, right? I need not write it. It's already there. So the aim is to increase this for my data. Okay. How will I increase this? I will take one step to bring this here. Okay. and I will take next step to increase this. Okay. So once you bring this here, it is same as the likelihood, log likelihood. If you increase this, then if you make sure that you increase this, then this also must have increased. And that's all you're doing. This is the expectation step. This is the maximization step. Okay. So in the expectation step, you make sure that you make the KL divergence 0. Okay. And therefore, your elbow exactly matches uh, your log likelihood. So to make this KL 0, the only thing you have to update here is Q. So here Q will be updated and theta will be fixed, right? And once you have gotten here, now you need to find theta, right? So in obvious, I mean, this is obvious, right? Because your log likelihood is actually a function of parameters, not of data samples. So at M step, you have found some Q, right? So that becomes Q dash. Take that Q dash and find a new theta, which increases this. So, and keep on doing this iteratively. So you do this, then you do this, then you come back and do this, and you come back and do this, right? Every time you will have a new theta and a new q doing a ping pong, right? So this picture actually gives you a much better idea of what is actually happening. So let us write all this down formally in the next slide. Okay, I'll come to that slide later. All right, so let us finally define based on the diagram that I had shown on the previous page. Let us define the E and M steps of the algorithm. All right, so let us just formalize this in terms of equations. So I again have the same figure here, right? And we have this as uh, we have the elbow and we have the log likelihood here. And this obviously is the KL term. Okay. So we are finally in a position to define the E and M steps of the EM algorithm, right? So you have your log likelihood, which is the sum of your elbow and the KL term, right? So in the E step, what you will do is you will reduce the KL to 0. Okay, so the way to reduce the KL to 0 is just explicitly set Q of Z same as P of Z given X. Okay, so because that is what the formulation comes out. So what happens in case of GMMs is that this P of Z given X, right, it is computable, right? So what you are saying is that if you are given an X, okay, what is the probability that it came from the kth z, okay, and that you can directly compute. Okay, so you have the current parameters which are given. So here I have just assumed theta k theta j to be the mean and variance, and pi I have taken separately. If your all your data samples of x are given, okay, what is the probability that the how many of them cause the kth z to be 1? Okay, that will basically, this is what is called as assignments, right? The gamma parameters, so the assignments of z. So these are explicitly computable. But effectively, if you see, right, all you're doing is you are just computing p of z given x. Okay. So once you compute this p of z given x, right, what you are doing is you explicitly set qz to p of z given x here. You set it p of z given x here. So this thing goes to 0. Okay. And once this thing goes to 0 in your E step, for a fixed theta, your elbow has come here. Okay, so after a certain E step, okay, after E step has come here. Okay, so now since it has come here now, right, you have updated the Q of this elbow. This Q has become some P of Z given X. comma theta. Okay, so a lot of times, this is also, let me write it like this, is also written as theta, theta dash, or something like that. So that becomes confusing. Okay, this p of z given x is a function of current thetas. Okay, and what you will do after the e step is to get the new theta, right? So anyway, the idea is that the scale divergence has been reduced to zero so that your elbow becomes equal to the log likelihood. Okay, so so that's what I said, and now you find the new theta dash, right? So now you have p of z given x comma theta. You want to maximize this. Okay, this is a completely computable quantity. Okay, you are here and you maximize this. So in case of GMMs, right, that maximization, the equation that comes out, you can work it out or look at uh, reference material. It's a slightly long derivation, but basically a mathematical derivation only. You just need to take derivatives and maximize, and you will see that your mu of k is going to be given by this in case of GMMs, and this is the covariance, uh, the number of samples in the kth for the corresponding to the kth latent, and the prior probabilities of the kth latent. This is p of z's which are there, and then you keep on doing these steps till you have very minimal increase in the likelihood. Okay, now it can also be shown that so it's basically obvious, right, from this figure that at the end of each step the elbow was made same as current log likelihood. Okay, and the at m step we always do a maximization. Okay, so during that m step, right, it is not possible for the log likelihood to decrease, right? It may happen that after maximization you still remain at the same place. I mean, the theta is such that the elbow cannot increase further. So you will remain at the same place or you will increase. So what EM does is it guarantees that the likelihood will not decrease. Okay, it may not increase monotonically. It may say remain the same, but it will not decrease. Right. So there's a pretty famous figure that is there for this kind of optimization. If suppose this is your actual log likelihood, what you do is at a certain theta, right? You first uh, get the elbow to come here, right? And then what you do is you do a maximization. So theta basically shifts here. Okay, so this is your new theta. So you will basically have something like this. Okay, there will be a gap now. Okay, again, so here what you did was you made it same as as the likelihood, and then you updated the theta, so the theta came here, theta dash. Okay, and now you again you take the e step and it will become same as here. You again compute theta and theta will come here. So you essentially keep doing this and keep tracking the likelihood and updating theta. Right. So it's this is essentially what I explained. Okay, we want to climb the log likelihood mountain, ln of p of x of theta, and it is a complex function. It may not be a simple increasing or decreasing function. Okay, so the elbow is the lower bound. Okay, it is a curve which always sits at the bottom of the log likelihood. So the e step will reshape the lower bound, choose a new q so that it touches at current theta, whereas the m step will update the theta. Okay, so that we can take another e step and find whether it is further increasing. So uh, so like I said, and also what we saw from the figure, it is almost guaranteed that the likelihood will not decrease. It may not increase, but definitely will not decrease. Okay, so this is also something that I had explained in the beginning of this topic. The responsibilities are soft cluster assignments. Okay, what is the fraction of the points n, that is the xi's, which belong to z is equal to k. Okay, so So the M step will refit each of these Gaussians. In fact, it can be shown that if suppose your GMMs are such that they are single discrete distribution centered at each data point, then your expectation maximization will lead to k-means. Becomes a hard cluster assignment. It's a very simple problem to show if your GMMs have a specific form when you are fitting to do the data. So you basically take one Gaussian for each data point that you have, right? And that Gaussian has infinitesimal variance. So it is exactly a very sharp distribution centered only at that data point. In that case, if you do EM on that, you'll end up with k-means. Okay. Right. So I have not talked a lot about why GMMs are so important, except for the ideas, the underlying ideas that are used here. Before I cover this slide, I would also like to say that GMMs, for example, in automatic speech recognition, were quite popular till deep neural networks came in. Till for example, you once you started having RNNs and LSTMs and so on, and now, of course, you have speech LLMs as well. GMMs used to be the go-to modeling architecture. In fact, GMM HMMs used to be the go-to modeling architecture in which the internal state of speech used to be modeled by HMMs, which are hidden Markov models, and the output, the distribution of the output. So, for example, if you break down the speech into different audio units, phoneme units, then the distribution of the output used to be modeled by a GMM. So, this combination used to be the state of the art at some point in time. Anyway, coming back to this slide as well. So one special case of using GMMs in case of discrete data. So in this case, my xi's themselves are discrete, are when you use PLSA, which is probabilistic latent semantic analysis. Okay, so it is a discrete mixture model, and it can, similar to GMMs, it can also be it can be trained as EM using EM. So now what you're looking for is a distribution of words given certain documents. Okay. So what I'm saying is that my latent variable is a bunch of topics. Okay. And there are total capital K number of topics. And for a certain if a certain topic is selected, then the distribution of words will be P of W given Z. Okay. So for every document that you have, right, you can model this. Okay. Don't get confused by this conditioning. What it says is for every document, you have a GMM setup. Okay. So you have for every document some latent distribution of topics, and corresponding to those topics, you have a distribution of words, right? So like I had introduced, this is exactly as P of Z and P of X given Z. Okay. The only thing is that in this case, right, this P of W given Z equal to K is also going to be a discrete distribution. It's not going to be this normal distribution. And again, your training can proceed with an identical logic as we saw in expectation maximization. All right. So this brings us to the end of the second module in this unsupervised learning topic. And let me just briefly go through the summary, and I'll talk more then. So GMMs can be used to model arbitrary densities, and they can also be seen as a member of the family of latent variable models. Uh, Although we worked with Gaussian mixture models, and later I just gave you an example of a discrete mixture model, other forms of mixture models can also be made. So you can basically mix simple statistical distributions with some weights to get other forms of mixture models. In general, most latent variable models will have expectation maximization as an iterative method for doing maximum likelihood estimation of these models. Like I said, EM guarantees a monotonic non-decrease in likelihood, which means that the likelihood will never decrease, okay? But it can converge to a local optima, okay? It's not guaranteed that it is going to find the best theta star that we were looking for. Only thing is, it is going to find a good enough theta star, which may be a local optima, okay? So now, if you notice the GMMs and the EM that I introduced, right? It was with discrete latence Z. Okay, so you had some ZI, okay, and those ZI were then linked to some normal Gaussian distributions, right? So you had something like this, and so your ZI, you will take one, you'll just pick one value of ZI, and from there you will use a certain normal distribution to have a continuous X sampled from it, right? So with this kind of a Gaussian mixture model and the EM algorithm, everything was completely tractable. In fact, you get direct equations to compute this mu k. Sorry, this should covariance and this one, right? So you get a complete equation to be able to compute this in an iterative way. But when z's are continuous, right, this likelihood is not computable. It's not computable. uh, you can't do expectation maximization to find the values of parameters and so on. Those kind of things are there. uh, I already talked about PLSA, and what you will see is that variational autoencoders are essentially the framework which also optimize elbow and where sets are continuous. So we will talk about it later. So it essentially tries to do the maximum likelihood estimation using a lower bound for continuous latents Z. Okay, and uh, the deep neural networks help in doing that. Okay, so they are not the fundamental thing in VAEs. They are used as an estimator. We'll talk about that. Fine, that's all on module 2 of unsupervised learning. Thank you so much.